Okay, so today it's a great pleasure to have Nima Rasekh from EPFL, and he's going to tell us about topological Hochschild homology and shadows of bicategories. So Nima, please take it away.
Thank you very much. So before I start, I want to thank the organizers for inviting me and giving me the opportunity to speak here. And I want to thank you all for attending. So this is a talk, as the title suggests, studying the interaction between THH and shadows. And everything new I'm going to say, just I said once for all, is joint work with Catherine Hess, who is also here at EPFL. So as the title suggests, I want to better understand how topological Hochschild homology relates to shadows. Now, I don't want to assume that you all know what these two things mean. So a large part of the talk will be actually reviewing these two concepts and kind of also give a motivation why we would study them in the first place. And then, yeah, I get to the main result where I relate those two in our most recent paper. And depending on time, which I'm quite positive, just to make sure, so I have 60 minutes, right? I should have asked this in the beginning, but
yes, yeah.
Okay, perfect. Yeah. So yeah, depending on time, then I will discuss some applications and then possible future steps. And I will try to give some details, but obviously not every detail can be presented because it's just a 6-minute talk. So for any further details and discussions and precise proofs, you are more than welcome to check out the paper that is on the archive. And you can also ask me, of course. So during the talk, feel free to ask any questions if you want. I will try to answer them as good as I can. All right. So let's start with Hochschild homology. So what is Hochschild homology? I start with some associative unital algebra over some ring, and then take some module M, a bimodule. I don't assume it to be commutative, and then I can construct this complex that is, well, has the shape that you can see. And technically, I'm kind of lying a little bit because I used the word complex, but really what I wrote there is this simplicial diagram. And what we recall here is that for every simplicial abelian group, I can construct a complex out of it. And let me recall the definition. So what we do is we just take the boundary maps that we had and just add them using alternating signs. And now this will, as a matter of fact, be a complex. So you can check that d squared, as a matter of fact, is 0. So using that, I can now compute the homology of this complex. And the homology of this thing is called Hochschild homology. And so as a sample computation, I can take the 0 Hochschild homology. And well, how do I compute homology? I compute the kernel and then the image and divide. And the kernel of the 0th thing is itself. And the image of the previous map is precisely kind of measuring how commutative the action is. So it's the commutator subgroup. So in other words, the 0th Hochschild homology is precisely telling me whether the action of A on M is commutative or not. So before I move on, I don't want to assume that everybody is familiar with Hochschild homology. I don't know, maybe everybody is. So if you are, you can tell me. But if not, I want to kind of give you kind of a heuristic, because I will assume everybody is familiar with a tensor. Because I think tensor products of abelian groups are a more familiar concept. So I can take two modules, like an AB module and an BC module, and then I can tensor those, where I have the standard tensor product over the ring B. And that gives me some kind of AC module. And I don't want to give a precise definition, because that's not the point. But one thing I can think about is I'm more or less taking some kind of product, but then I want to quotient out by this action here, where I say if I multiply B to element M on the left, that should be the same as multiplying the same B to N on the right. So I'm quotienting out the B action that's kind of sitting in the middle between M and N. And that's kind of one important aspect of how to obtain the tensor product of two modules. Now, Hochschild homology is kind of like tensoring with itself. Because what I'm doing now is I'm taking M itself, and I'm quotienting it out with respect to the action, which says, well, AM is equivalent to MA. So here you can kind of see the analogy where like I'm an A action on both sides, and I'm quotienting out A from one side with itself. So it's like almost like you're tensoring M with itself and then kind of quotienting out. And so it's like a derived multiplication with itself, if you want to. And there's a nice picture you can have in mind for this that might be helpful. So I want to think of an A, B module as some kind of line between the two rings A and B. So, and the tensoring is quotienting out the B action in the middle. So I have like a tensor here, and that gives me this picture. Right, so I still have my AC action on the sides, but the B action is gone. It goes quotient out by the tensor. Now, similarly, if I have an AA module, M, then applying this Horseshoe homology, it just kills all the action. So what I'm left with is just an abelian group with nothing else. So it looks like there's no action left anymore. And that is like, so if you're familiar with Horseshoe homology, great. But if not, maybe this kind of can help you think about it as you have some kind of tensoring with itself, but in some kind of homotopical way, but there's still some non-trivial self-identification happening. And I hope this helps. All right. Having said that, why should we care about Horseshoe homology? So one thing that we can show is that if you take A to be a commutative ring, and then commute the first Horseshoe homology, then this recovers the so-called Kähler differentials of this commutative ring. And why is that important? So very small algebraic geometry notice. To every commutative ring, you can associate the so-called affine scheme or like a variety. And those are kind of like geometric objects. Now I want to compute kind of the geometric properties of this topological space, the variety. And one of the important ones are precisely differentials, so Kähler differentials. And they can be recovered from these Hochschild homology. In particular, then I can think of Hochschild homology of a non-commutative ring as being like the Kähler differential of this non-commutative geometric object, if it existed. And so this is precisely of interest to people who really like non-commutative geometry. A famous example being Alan Korn. So and so you can find kind of Hochschild homology in the work of the non-commutative geometry people. However, I'm a homotopy theorist, and I will assume a lot of you in the audience are also homotopy theorists, or at least like homotopy theory. So we might ask, okay, why would we care about this? Like, where does it come up here? And a key motivation for this is the algebraic K theory. So I'm not going to get into too many detail about algebraic K theory, because that would be its own talk. But just to summarize, it's a powerful invariant of a bunch of things. You can plug in a ring or certain categories or spaces, a lot of things. And the resulting algebraic K theory has connections with a lot of mathematics. It shows up in stable homotopy theory, it shows up in algebraic number theory, algebraic geometry, it's everywhere. And so then the key question is, how can we compute it? So whenever an invariant is interesting, we want to compute it. And unfortunately, whenever an invariant is interesting, it's also very difficult to compute. So the first thing we do when we can compute something is approximate it. And one of the kind of interesting results is this so-called Dennis trace map, which approximates algebraic K theory via Hochschild homology. So that kind of then made Hochschild homology an object of interest in the world of homotopy theory, because computing Hochschild homology of rings can kind of help us better understand the algebraic K theory of the ring. And one of the first kind of steps then by the homotopy theory community was to generalize this construction of Hochschild homology from just rings, which are like discrete objects, to ring spectra, which are the key objects in stable homotopy theory, which is what I will go to next. And just a historical note, this was first done by Bergstedt, but the presentation I give is, for example, already EKMM, so which goes back to the late 90s, more or less. So how can I define the topological Hochschild homology of a ring spectrum? I more or less repeat the first slide of the talk, where I now replace every ring with a ring spectrum and every bimodule of a ring with a bimodule of a ring spectrum. And now I don't want just the homology of a complex. I have now a simplicial spectrum, and I want the geometric realization of that. And now it's a really big benefit that I started with this simplicial diagram in the first place, and not just with the complex, because the complex version does not generalize directly. I don't actually know if everybody is familiar with spectra in the audience. Is that a reasonable thing to assume? I should have maybe asked, but okay, like I see affirmative head nod, so good. I will assume everybody's familiar with spectra. And I'm not going to do too much with spectra. So if you just know spectra, some kind of stabilization of spaces, then that should suffice for the purpose of this talk. So yeah, I can just define topological Hochschild homology of the module M over the ring spectrum A by taking generalization of this thing. Now, actually, I want to do a little bit better. I don't just want topological Hochschild homology of rings. I want to generalize this to categories. And that is because algebraic K-theory is defined for a variety of categories, actually. And there are several things you can plug in. One famous example are these so-called Barthausen categories. And there are also other examples you can use. So what you want is THH of some categories. And the example that I want to focus on here is the case of spectrally enriched categories. So as a spectrally enriched category, it means I have a category in the usual sense with objects, but then instead of having a set of morphisms, for any two objects, I have a spectrum worth of morphisms. And then the composition is given by smashing. And how does this relate to my previous example of a usual ring? Well, I can just, if I restrict to a spectrum enriched category over one object, then that is precisely the data of a ring spectrum. So the slogan is a ring spectrum is a spectrum enriched category of one object. And now what I want is I want to generalize my definition of, so I want to generalize this definition here from just a module over a ring spectrum to a bimodule over a spectrally enriched category. And so the way we do it is by using the following approach. We define this thing like a bimodule here. And now if I have a CC bimodule M, i.e. a functor from C up times C into spectrum, then I can just define my THH by using a very analogous formula here. And here you should imagine is each one of these are kind of like a ring spectrum. And I'm smashing them together, but then I'm keeping track of the objects. So in particular, if I only have one object, then this exactly recovers the previous formula. In every C, every one of these would be equal, and it would exactly be just saying I have a ring and I have a module, and just take THH. So this is kind of the generalization that I want to focus on, this THH of MC, defined via this equation. And one key property of this THH of MC is that it has this nice kind of commutation property. What do I mean by that? So if I have two modules M and N, so now M is a CD bimodule and N is a DC bimodule, then I can compose them. And this composition here, so this is given by some kind of coend here, or if you don't like this, you can think of like a two-sided bar construction. So depending on which kind of stuff you're more comfortable with. But the key is you have like a D action on both sides, you're portioning it out. And so using this, you get like a tensor product of bimodules. And now I can also reverse this, and I can also tensor product tensor N and M. And then the cool fact we have is that we have this equivalence, where THH of M tensor N is just THH of N tensor M. And before I want to move on, this is a really important property. So I actually want to try to explain why this is true, to give you maybe an intuition why, if you take THH of a tensor product, you kind of can reverse things. And for that, it's helpful to remember this kind of nice picture I drew before. So if I take a module, an AB module, and an BA module, then what I discussed before is I can imagine them as being this line between 2 points. So I have A and here I have M and N, two modules sitting between the rings A and B. And now there are two things I can do. I can either tensor over B, or I can tensor over A. So if I tensor over B, I quotient out the B action, and what I'm left with is kind of this picture. So I still have my AA action, but the B is gone. And so now this is M tensor over B, or I can tensor over A, and I keep my BB action, but then I have M, oh, wait. Here, this should be N. Because yes, exactly. So I have M tensor N and I have N tensor M. And now I have here an AA module. So what I can do is I take THH of A, or here I have a BB module. And so I can take THH B dash. And in both cases, I end up with nothing. I just quotient out all the actions. So in this case, I get THH of, I think at this, I should flip this. A is here. So I have THH of M tensor N, A, or THH of N tensor over A and B. And the statement is these two are equivalent. And how should we think about this? In both steps, we're quotienting out certain actions, but we're just commuting the order in which we quotient them out. And if you think about it, that action should be commutative. Quotienting out actions should be a commutative action. It should be a commutative operation. So this is not a proof, but it might help to give you a sense that in both kind of steps, we're doing certain quotient operation by an action, and that should commute. So we have this result: THH of M tensor N and THH of N tensor M should coincide. So before I move on, let's look one last time at this slide. If you notice, there is a lot of notation. There's like spectrally enriched categories and smash and tensor and geometric realization and all this stuff. And in order to use this THH, you need to know all of this. And that's getting annoying and tricky. And what we want is a more kind of streamlined, cleaner form of this. And what do we do whenever we want a more clean version?
Sorry, can I ask something?
Yes.
Before you go on. So when you have a bimodule like this, COP smash data spectra, can you represent the bimodule by like another spectrally enriched category which includes both C and D?
Can you represent M by a spectrally enriched category which includes C and D?
Yeah, and the
like a correspondence kind of
yeah. Is there such thing for?
I think so. I mean, I'm not using it, but I mean the same principle. I mean, I guess okay, it's wide in spectra. So yeah, so obviously the answer was if it was wide in cellular spaces, then yes. If it's wide in spectra, then you have to think a little bit how to make this work. So I'm not sure. It doesn't show up here, so I haven't thought about this. But so this is like, I mean, so you're talking about like an enriched correspondence. Which,
right, something.
Yes, I mean, I think for spectra you should be, but I've not thought about this, so I cannot give you like a definitive answer here.
Okay, thanks.
No, sorry, like I don't, yeah, because I've not thought about this too well, but yeah, so I can't give you like a certain answer for this. So hope this helps. Okay, any other questions? All right, then yeah. So look at the slide. This is like a lot of mess. So what we want is a more kind of cleaner version that has the same implications. And how do we do this? One effective way of doing this is by category theory. So you find kind of like a nice categorical axiomatization that is able to capture the relevant information that we need, and then we use that to kind of prove what we want. So that's a very kind of common application of categories, right? You want to study homological algebra, you use an invariant category or something. You want to study certain kind of higher categorical features, like infinity categories or something. So, but we wanted something similar here. And the key kind of player in this will be bicategories. And while I'm comfortable assuming everybody knows what a category is, I don't want to assume everybody knows that well what a bicategory is. So let me like very carefully review all the data of a bicategory and then get on to the key definition. So for me, a bicategory has a collection of objects, so X, Y, Z, so on. And then for any two objects, I have a category of morphisms. So it's a really important key property of this is that for any two objects, I have a category word. And then for any three objects, I have a normal composition. And I have a choice of identity object sitting inside the category BXX. And the key differences then with the more usual notions of strict two categories is that my composition operation is neither associative nor unital. It doesn't have these properties. Rather, there is a natural isomorphism between, for any three composable morphism, there's a natural isomorphism from the one composition to the other one that is known as the associator. So it's telling me it's associative up to natural isomorphism. And similarly for the unit. So there's the unit, it's not a strict unit, rather there's like a choice of right and left uniter. And then telling me that if I pre-compose with the unit, I'm just naturally isomorphic to the thing I started with. So notice every kind of category is an example of a bicategory where, well, the associated and unit are just the identity. So if you are strictly associative and unital, then yeah, it's fine. But you have examples of bicategories that are not. So with that in mind, we can get to the main definition, and that is that of a shadow. So a shadow was introduced by Ponto, okay, Ponto, who was exactly studying kind of THH and fixed point phenomena, other stuff. And she wanted kind of like this more abstract, streamlined definition that is able to capture all relevant data that we have just seen before. And so how is a shadow defined? We start with the data of a bicategory B and a category D. And now a shadow is a collection of functors. And the key thing is, remember again here, this is a category, right? So for every X, BXX itself is a category. So I have a functor from BXX to D, a collection of them for every object in B. And then I have this natural isomorphism from the shadow of FG to the shadow of GF. So it's like this twisting isomorphism. And this data needs to satisfy some kind of nice compatibility axioms that I will just like show you. But you don't have to like memorize this, so don't worry. There's like some kind of nice appropriate kind of compatibility with the associator and the uniter and so on. But the key thing to remember about this definition that I will require is there's a collection of functors from the endomorphism categories, and there's this nice twisting isomorphism that flips things around. All right, and so everything I have said up until now, you would assume that I have an example of a shadow in THH. So it would be quite a shock if I now announce that it's not an example. So I will not do that and not be shocking and give you the relevant result. That is due to Campbell and Ponto, who in a paper from 2019 proved that if I take mod to be the bicategory with objects spectrally enriched categories and morphisms are exactly the homotopy category of CD bimodules. So an object here, like an object in this category is a CD bimodule. So in particular, then mod CC are precisely the CC bimodules, and THH is a functor from the CC bimodules to spectra. And it exactly satisfies the axiom of a shadow. In particular, the twisting isomorphism is induced exactly by this equivalence that I talked about. So this definition of a shadow, which is like seems very abstract as a level of bicategories, captures a lot of the data that we need. Let me illustrate this claim by one example, namely a cool example like Morita equivalence. So what is Morita equivalence? First, I'll remind you what a Morita dual is. So for a given bicategory, I can say two one morphisms F and G are multi-dual if I can find like a diagram like this, satisfying the classical triangle identities. So this if this reminds you of the adjunction diagram, then because it is the adjunction diagram. So I'm just saying I have like an adjunction diagram in the bicategory B, similar to how you would in the bicategory of CAT. So in CAT, this would just exactly be the definition of an adjunction and nothing else. The reason it's called Morita dual is because this is motivated by rings, and there C and D would be like the category of rings, the category of modules over some rings, and then this would precisely be the notion of a Morita dual of like rings. And so this is called a Morita equivalent if U and C, the unit and co-unit, are isomorphisms, which is exactly correspond to adjoint equivalence. Again, if you move comfortable categories, you can think of that. And so one thing that Campbell and Ponto prove holds at every shadow is that if I have a diagram like this, if I have a diagram given to me like this, so that U and C are in fact isomorphisms, then computing the shadow on identity of C and the computing shadow of identity of D, over which are isomorphisms, is in fact isomorphic. So we don't need any of the specifics of THH. We don't need any of this stuff about spectra enriched. We don't need any of this. Just by saying we have this functor from these endomorphism categories, this twisting and subcompatibility, we get this very classical result of Morita invariance, which was known for THH already, but holds in this much more general sense. So this is like a kind of like nice example where I give like semantization and I recover exactly the properties I want, without having to bog down too much by notation or stuff. All right. So with this, I'll stop for like 10 seconds. And if you have any questions, then feel free to ask. Because I'm more or less done with the review part of the talk.
Oh, okay. So the Campbell-Ponto results that you stated, they don't use that language, right? They state these in a more classical way.
Wait, so Campbell and Ponto, they state things in a more which classical way? What is the more classical?
So I think they're looking at these module categories, right, over a ring spectrum, and so this statement that you're, this theorem, which theorem does it correspond to in their work? Is that the equivalence between the THH of the module category and the ring, or?
This, I mean, I don't know the number of the theorem, so I can't, but it's like in section, I want to say the end of section 2.
Oh, okay, it's not the main result then.
It is not the main result.
Oh, okay.
I don't think so. It is, I mean, this statement exactly as I stated is in a paper, without, I mean, yeah, so I mean, it's phrased a little bit different, but it's exactly this. I mean, they exactly use THH as a shadow. With that phrase.
Okay, so can you just say, repeat the morphisms here? Mod CD is equal to?
So mod CD is a category, and the objects in this category are precisely these kind of functors. Okay, so to be like a little bit more precise, there's like some, I mean, this is like, so they use model categories, of course, because, and then when I write homotopy category, then you have to be careful. You need some covariancy conditions to make this like this smash product work and stuff, which I don't want to mention here for the purpose of the talk. But yes, if you want to make it precise, because you're taking the homotopy category, so because C and D, so mod CD has a model structure. So the bimodules come in model structure, you want a homotopy characteristics. So you need some condition here, and then everything else is it's the same. And then you exactly, so in particular, if you take mod CC, an object is precisely a functor from C of C to spectra. And then THH is defined precisely as I defined it here. This. So I want precisely this THH. I think this THH here, that takes a module over C to this spectrum. This is in spectra, right? Satisfies the Isomorphism shadow.
Okay.
And the key point to check is exactly that this weak equivalence here will induce this isomorphism here, right? Because an equivalence at the level of spectra gives us an isomorphism in the homotopy category. And then, okay, then the rest of the work is to show that it satisfies some conditions, and yeah.
Okay, thank you.
Yeah, so it is in their paper, basically stated exactly as I said. Any other question? Okay, then I shall move on. So the overarching goal of the thing that we are doing is kind of to take steps and infinitize everything in some sense, or make everything homotopy coherent if you want to. And the first question you can ask is like, why? Why do that? Like, so you want to move away from certain like homotopy category or model category constructions to just more general frameworks. And while I think it's kind of a cool just to do it, but I think there are also like several kind of valuable justifications why this is a worthwhile project. The first is that so I use the shadow right now to show I can understand THH. And to be clear, I mean, this result here I showed is like one of a lot of results. So like Campbell and Ponto kind of show very extensively that shadows satisfy a lot of properties that you can find in THH. And then you can use this kind of to understand THH better. And this is like just one example of that. And so the question then is, why is that possible? Like, why is it possible that if I start with this abstract definition just on a bicategory, can I deduce all these properties about THH? What allows it conceptually to have this kind of power beyond just knowing it by proving it? What is happening there? And are there other functors other than THH that I can recover using similar methods? Is there something specific about THH that is recovered with shadows? Like, what is the connection there exactly? And this is hard to study by model category techniques because it's hard to manipulate kind of model categories as a collection sometimes. So that's one way. That's one thing that prevents it like from being studied using model categories. Another reason that is actually getting more convincing is that, well, the same way that there are all these like definitions of THH at the level of homotopy categories, and shadow is able to like kind of incorporate all of those and study and compare them. There's now a lot of definitions of THH at the infinity category level, right? So there's this really like extensive paper by Nikolaus and Scholze, where they study THH of rings, and specifically really study the cyclic action, the cyclotomic action, so to speak. There's a paper by Berman, which studies THH of enriched infinity categories. And there's like a series of papers by Ayala and Francis. So they don't specifically study THH, but they do study these things called like factorization homology. And factorization homology evaluated at the circle covers THH. So then there's all these like definitions of THH at the level of infinity categories. And the same argument, you could ask yourself, okay, how do they compare? And can we just use one framework that helps us understand all of them at once? And the last one that I would say is actually the most convincing is, so there's a notion of topological Cohort homology. And in order to make sense of it, you can just go to the first slide of this talk and put a co in front of everything. So you can start with a co-algebra, and then you get like a co-simplicial object, and then you take the totalization of this co-simplicial object, and that will give you like topological Cohort homology. And then you can start studying it and computing it, and ask yourself, okay, given a certain co-algebra, what is the co-THH of it? And this was, I think, first defined at this level by Shipley and Hess. However, the realization now is that we cannot compute this co-THH just using point set level models of spectra, right? So we cannot use the kind of classical model structures of spectra the way we use it for THH. And the reason is that recently in a paper by Peru and Shipley, so they show that if you take any of the standard models, the point set models of spectra, so like symmetric spectra or orthogonal spectra or any of these models, and then look at the co-algebra object in it, then it will be very restrictive. But it will be in some sense like it will have an epi map from a suspension spectrum. So in particular, it will always be commutative, a co-commutative, because it's a co-algebra. And that is not what we want. There are lots of co-algebras that should not be co-commutative and that we want to study using co-THH. And so because of this, then the only way to make this work is to use some kind of infinity categorical model of coalgebra objects in spectra. So in particular, then whatever definition of THH or shadow you want to use has to be at that level. It cannot work at a pointed level. All right, so I hope you find at least one of these three to be convincing. And having said that, let me move on to necessary definitions to make sense of the result. So I want to define what THH of a bicategory is. So this is a little bit kind of confusing because THH, to notate THH is used for a lot of things. So just to like make clear, I'm defining now for you something where like I start with THH and in the input is kind of like a bicategory. And the output of this is a category. So this is kind of like what's happening. So I put bicategory into THH and get a category out. And how can I do that? So then THH is defined by, well, just using the standard THH formula, but on the mapping categories. So I should note, so here this is true by definition. I'm just using this notation, this kind of BX0 to XN to X0, just to mean this product, because I don't want to write the product every time, because it gets tedious. And now an observation is that this is equivalent to this particular colimit. So I have like 3 levels in my, it's like it's a simplicial diagram, but it's truncated at level 2. So I have 0, 1, and 2, and I don't need the rest. The key thing to remember about this colimit is that it's a colimit inside the so-called 2-1 category of categories. So the terminology is a pseudo colimit. Right? So I'm not taking a colimit just in a category of categories, I'm taking it as a pseudo colimit. That makes it vastly more complicated, just to keep that in mind. So the computation is not just the easy co-equalizer, the way you would think of it. It corresponds, if you're familiar with model categories, it corresponds to taking the homotopy colimit in the canonical model structure on the category of categories, if that tells you something. So all of these are the same, like a pseudo colimit or a 2-1 colimit or a homotopy colimit. And so then I call a functor from THH of B, which is a category, into any other category D, a bicategorical trace. So this is like by definition. A bicategorical trace is a functor from the category THHB to D. All right. Are there any questions? Nope. Okay. Then this is like one side of what I need to understand. For the other side, I already defined for you what a shadow is, but what I really want is a category of shadows. And in order to get a category, I need morphisms. So a morphism of shadows, so given 2 shadows, which like a shadow 1 and shadow 2, a morphism is just a natural transformation that commutes with everything inside. So it has to commute with the twisting isomorphisms, but it also has to commute with the associated unit. So it's a very unsurprising definition, I would say. And now the main result that we prove to understand what shadows are, how they relate to THH, is the following, namely, if B is a bicategory and D a category, then there's a natural equivalence between bicategorical traces, i.e. functors from THH of B into D, and the category of shadow functors from B into D. So in other words, a shadow on B is just a functor out of THH of B. That's kind of the gist of this result. And notice I wrote this equivalence symbol, but they're actual functors in both directions. So it's a very kind of concrete construction going from one side to the other. I don't want to give a very detailed proof because that would be boring. But let me give you like a sense of what's happening. Okay, I think that question.
Sure.
Yes.
So this is still, I mean, like in the bicategorical framework. So you haven't.
Yes. So wait. I mean, these are categories. So wait. Yeah. B is a bicategory, and these are categories.
Yeah. Yeah. I mean, like the statement of the theorem. So it's not like higher categorical. I mean, it's higher categorical because it's bicategories, but.
Yes. No. It's not infinity categorical.
Yeah. Not. Okay.
I mean, I want to use this result to then define a set of infinity categories. But yes, this is not yet. No.
Just to clarify, when you say the shadows taking values in D, you mean the collection of functors are in D, right? Taking.
I mean, so an object, this is a category, okay? An object is a shadow functor, a shadow functor from B to D. Okay, which, I mean, remember what is a shadow? A shadow is a collection of functors.
Okay, okay.
From this endomorphism of Bxx to D, and then the twisting. So I'm saying an object is this, and then a morphism is like this natural transformation between two shadows.
Okay, okay,
Right?
thank
So
you.
it's not a direct functor, right? The objects are these like weird shadows as defined before.
So so this theorem, I mean, you're looking at functors from the THH, which you defined as a pseudo colimit,
Yes.
right, into D. So would we say that this equivalence is like the universal property of that pseudo colimit? Like,
Yes, we could say yes.
I mean, it's like the collection of functors from the pseudo. Yeah, because I mean, when you do the shadows, you have that compatibility condition, etc., etc. So if you collect those into diagrams and look at that.
Yes, that's my next slide, I think. You're just
Okay.
describing my next
Okay.
slide. Yes, exactly. Right, that's
I mean, okay, it's natural, right?
Yeah, so any other questions? Yes, let me tell you the next slide, and then maybe this probably address your question. I mean, anyway, I think you're exactly on the right path. So let me like understand this equivalence better without giving like a complete proof. And so one side is actually not that hard, and that is so this side, and exactly as just pointed out, if I've been given so how can I construct an equivalence between those? On the one side, THHV is defined as a colimit. So by definition, a functor of a colimit is a functor of the cocon. But everything is pseudo, so we pick a pseudo cocon. And so now what I'm telling you is, okay, if I've given a functor like this, I have a, by definition, I have a pseudo cocon that looks like this. And what I want is to get a shadow out of it. That's kind of like the gist, right? Like, how can I construct a shadow out of this pseudo cocon? And the trick is just look at it and then do it. There's no trick. Namely, okay, can just say this is precisely a collection of functors from the endomorphism categories to D. And now I need a twisting isomorphism. Right? That's the second part. And how do I get a twisting isomorphism? Well, I know that if I apply D0 to an object here is precisely a functor, a morphism from x0 to x1, and a morphism G from x1 to x0. And D0 just composes those. And then the C0 is precisely the shadow of FG. And on the other hand, if I take my FG and apply D1 to it, I get GF. Like that's how the boundary maps work. And now again, if I apply the shadow, I get the shadow of GF. And now the commutativity implies that they should be related, but they're not equal because it's a pseudo cocon, rather they are natural isomorphic. And so I just named that natural isomorphism data. And that is like the data of a shadow. Now what I need is I need to confirm that it satisfies the compatibility diagrams. And that is not too hard. You just look at like the rest of the diagram and then figure it out. So this is one side, like going from the pseudo cocon to the shadow is not too bad. So you have all this data and you just extract the data of a shadow out of it. The hard part is the other way around. So now the question is, for the other side, if I have a shadow, I want to construct a pseudo cocon out of it. And one way to think about a pseudo cocon is like I want to lift, I have this diagram given to me, I want to lift it to this kind of cocon. And so the claim then is that such a lift is precisely the data of the shadow given. So this is not straightforward. I mean, we kind of have to reduce you have to kind of figure out what the difference between these, like what is here happening, right? If we go from this truncated simplex category where I only have 0, 1, and 2, and then I add like one object and like exactly one morphism to it, what is exactly the data necessary to construct such a pseudo functor? And yeah, this involves kind of understanding, okay, how do we construct pseudo functors, which is its own like mess. And fortunately, like the so-called Australian school has thought about this a lot. And there's like these nice papers on like pseudo functors out of 2 categories, and so how to strictify them to certain 2 functors. So there's like model structures constructed by by people like Street and Lack, and using that you kind of can do this. But this part is the hard part, because a priori, I mean, there could be lots of abstractions. So it turns out there isn't really. The abstraction is exactly the data of this one map, and then this isomorphism, and then whatever the compatibility is. So it's like a computation at that point. So yeah, this is all I want to do about Ducoin. So now if you have questions about it, then feel free to ask, because I want to move on to the next part.
Well, so I think, okay, in doing this, you have sort of answered the question that you raised some moments ago of him. I mean, if I'm correct, like you said, like, why is this notion of bicategory with shadows kind of work? Right.
Yeah, that's my next slide. You're always one slide ahead.
Sorry.
Awesome.
Yeah. Okay.
That
okay.
is good though. This
no,
means,
I
like,
wanted to like see if I'm
yeah.
okay.
I mean, now I want to move on to implications. I want to make sure like everybody's had any questions about the argument, or I mean, you had some questions about this. No, this is good though. I mean, I'm happy. That means it makes sense. Okay, so then I want to move on to implications, and then to future steps. So first, let me look at implications, and the first implication is exactly what I just pointed out. The result precisely implies why is a shadow a suitable kind of definition to study THH. It is THH, more or less. It is co-represented by THH, right? It's like a functor, a shadow, like, so exactly what I'm saying is that in something SHA B dash, this functor is equivalent to functor THH B dash, right? So it's co-represented by a THH of itself. So of course, if something is co-represented by THH, it will have all the kind of properties you would like to have that come from THH. So, but this was not clear. So now, like, it makes perfectly sense why. So the way to think about this result is that the data of a shadow is something like a strictification of the data of a cocon. Like, it's minimal exact data where you pick. It's like, think of a CW complex where you take a minimal number of cells to recover the right motor loops. Right, so you pick exactly 1 0 cell and then like one loop or something, and then exactly enough compatibilities there to make everything work. That's a shadow. Whereas a cocon a priori has way more data. But then the argument of the proof is you can reduce it to that. And so this is a nice kind of interplay. So from that perspective, let me just say this before I move on. From that perspective, you can think of this result as having kind of like 2 sides, where on the one side, the equivalence is telling me that a priori this complicated colimit, I can exactly characterize it by this set of data. Like, if I want to construct an object out of a colimit, computationally, all I have to do is to give you a shadow. It's like way less data. And on the flip side, on the formal side, the shadow out of B is this functor out of the colimit. So it's like a computation versus formal kind of statement relation, the way I interpret this. Yeah, so now this makes perfect sense. And now I'm happy. At least that answered one of my questions.
Sorry, just
yes,
one short clarification. So the notion of a shadow, well, let's say when it was invented, did not have this theorem in mind. Did it, like, were they trying to just model the properties of THH, as you were saying?
Yeah.
Yeah, right. I mean, I'm just saying, like, this theorem was not perfectly in sight, sort of when shadows were defined.
I don't think so. I mean, particularly
Yeah,
because it's hard. It's even hard. I mean, sometimes it's also like the formalism suggests itself, but because you first need a good notion of THH of bicategories to even make sense of this. And this is like,
yeah.
people just didn't think of that kind of stuff. I think it's
Mm.
just not the focus at that point.
Okay,
So,
thanks.
but yeah, I think I guess if you have the right statements, then it's perfectly reasonable. But then, yeah, I don't know. This is kind of like math a lot of times, right? After you've done it, it's so obvious. But before that, it seems so complicated. But no, I mean, with the right framework, like if you phrase a definition appropriately, it makes perfectly sense that they fit together. Just it was like a question of like exactly finding the right definitions. So yeah, this is like so yeah, it's a little bit. It has the feeling of a formal result, but the proof is like highly non-formal. So no. The proof is really almost like obstruction theory. You just have to like show that all the lifts can be kind of fixed, but it has a formal feeling to it. I agree.
Yeah, two categories are a mess.
Yeah. Let me look at one other implication. For that, so in particular, like I want to focus on Morita invariance. So for that, I need to come back to the so-called free adjunction category. So let H be the free adjunction 2 category. And by that, I mean it's the free category, the free 2 category on this diagram that you can see. So it's the if you know what an adjunction is, it's the category you would think of, right? It has 2 0 cells, two generating kind of 1 cells, and then there's 2 generating 2 cells, and then it satisfies all the triangle identities and so on. And it has the universal property that a 2 functor from H into any bicategory B is precisely the data of a adjunction diagram. So in particular, if B is cat, it's precisely an adjunction of categories is precisely a 2 functor from H into cat. Now, one thing I can do is, now that I have this kind of understanding of shadows as THH, is I can look at THH applied to this functor category. So I get from HB and then apply THH to it. And so you get a functor. So this is like a functor of bicategories. These are like bicategories, right? Whereas these are like categories. So I have a functor that takes from a functor from H to B to a functor on THH H to THHB. And so as we established, this side has precisely the adjunction diagrams in B. And whereas this side has some diagram inside TH of B, which I don't know what it is. I want to use this functor to understand Morita dual pairs inside, like what they imply inside THHB. And for that, I need to compute this thing. I need to know what this THH of H is. What category is it? Turns out this is really complicated. So instead of computing THH of H in all detail, I want to compute THH of an approximation of H. Namely, I take H, but then I add 2 relations. Namely that if I compose L, R, and L, I just get L. And if I get R, L, and R, I get R. So like you impose these 2 additional relations on this. And then you can just sit down and work this out and compute THH of this category, this 2 category. And it turns out to be equivalent to the post set 0, 1, 2. So like follow up as I have 3 objects and I have like 1 morphism going like this. And moreover, there's an obvious projection map from H to this approximation because I'm adding relations. So there's a map from H to this H less than or equal to 0. And that has a section that I will need later on. Now I can use this computational result for a cool formal result. Namely, I can, starting from functor here, I can first apply my THH to get to THH and THHB. Then I can post-compose with my S, the section, right? Like S is the map I described from 2. I'm doing this, yeah. So from 2 to THH H. And then now I have like 2 morphisms here, so I can just compose them. to like one arrow. And the claim is that if you start here with this kind of like a junction data in B and trace through these steps, what you get is precisely the morphism that goes from here to here. I'm getting an arrow, right? I'm getting an arrow inside THHB, and my claim is that the arrow will be precisely this. That is the composition of like U and C inside my adjunction data. And so in particular then, if the adjunction I started with was an adjoint equivalence, i.e. U and C were isomorphisms, then the resulting thing will also be an isomorphism. This is just now functoriality, right? Functoriality tells me that if I functor from something to something, if I start with an isomorphism in the domain, the outcome will be an isomorphism. And so then using this, I get Morita invariance of my shadows. Because I'm proving that anything in THHB has this property, and THHB co-represents shadows. And so there's two cool aspects to this proof. And the first one is, again, this kind of like nice interaction between computation and formality, right? So the key input is the computation of this particular bicategory, and the outcome is a property about something, namely Morita invariance. And the second one is that this holds in other places. So I focused here in this talk on like bicategories, but theoretically you could do this with anything else. You could like enrich over something else and do something similar. It would still hold. It's kind of like a nice aspect. And so I'm also out of time. So let me like quickly get through my last couple slides. My last implication is that now I can use this definition to define what it means to be an infinity category shadow. So that's kind of like one of the key things that we wanted to do in the first place, is to define what does it mean for a shadow to be an infinity shadow. And now I can just say, okay, if I have an infinity 2 category B, I can just define a shadow out of B into an infinity category D as an infinity categorical functor from THHB to D. And notice these notions are in fact well defined. So I'm not discussing this in a talk because that would take us too far astray, but there is an appropriate notion of THH of an infinity 2 category, which in fact takes value in infinity 1 categories. And so the next step then is to construct interesting examples of that, which is not too straightforward because you have to deal with a bunch of coherences. One thing I will say here is that unlike the bicategorical situation, I don't expect there to be some kind of nice strict factorization, right? So if you want to think of this equivalence of before here, really what I'm just doing, I'm generalizing this part, right? I'm just generalizing this in the appropriate sense. I'm not generalizing this, and I don't think you can generalize because this kind of, it's like specifying the data necessary, like a functor and some kind of like natural isomorphism and compatibility. But if you wanted to do this with some infinity categories, you would have infinite layer of data, and this would never end. So this part kind of is, I don't think can be generalized meaningfully. In the last minute, let me give you two possible future steps. And as a matter of fact, here I write 3, but the last one I will not give too much detail about because it involves discussing co-THH, which I have not done in a talk. But you can imagine now that if I have this co-THH and I want some kind of infinity category shadow. But the thing that I can discuss is here. So now we've seen before, like, so what Ponto and Campbell prove is that there's a shadow on the module category. And if you combine this with our result, now you get this functor here, right? So there's lots of THHs here. So I hope this notation makes sense. But this is a bicategory, right? And I'm computing THH of this. So this whole thing is a category. And this corresponds to a shadow which they prove exists. So then by our result, we have a functor THH from the category THH of mod to SPIL. Oh, sorry, I meant here, sorry. I wrote this in the wrong place. So, yeah, whatever. I don't want to erase this anymore. But now the thing that I want to do is lift this from just a functor of categories to a functor of infinity categories and giving it the appropriate homotopy coherence. So that's kind of like the next key step. So that if you restrict to the homotopy categories, you get back what Campbell and Ponto proved already. So using this new notion of this infinite category shadow. And one kind of like key computational fact that you can also like try to tackle. Is there any question? Nope. Okay. So one key computational kind of thing you can tackle is, do we have a good notion of a bicategorical shadow? But if you want to study shadows amongst themselves, what you would like to have is a kind of tricategorical shadow. And now you can ask yourself, how would you define it? And the result we have basically implies that the data of a tricategorical shadow is precisely the minimal data required to lift such a thing here, to like a pseudo lift. So this kind of gives you a nice direct way to construct a definition by knowing exactly what universal property should satisfy. So I've not done this because that would be a cool thing to pursue if you want to study shadows and how they kind of connect to each other. And with that, I end my talk. And again, for more details, feel free to check out the paper, ask me here, or send me an email.
Okay, thank you very much, Nima. Okay, any questions for Nima? Okay, so the part that you were talking about, the last, I think it was on 32, page 32, that part was a bit quick for me. Could you?
Yeah, okay, yeah.
Just say what the goal was.
Yeah, so I have minimized this because I was like rushing this. Okay, so Campbell and Ponto prove there's a shadow from, so Campbell and Ponto prove there's an object inside this thing, right? Shad mod, if I want. So in like, let me like now think of mod as between two categories. So homod, spec. Right? So they proved that an object here exists. There's a shadow here. And now our equivalence then implies that there's a corresponding functor here that we call THH. So the homotopy or version of THH. And now the question is, can you lift this functor from the homotopy categories to a functor of infinity categories and make this current construction homotopy coherent?
Okay, but wasn't the original definition of Campbell and Ponto, was it from the module category to this category of spectra?
Yeah, so that I kind of changed notation when I got to the end of the talk, because I was using mod for the bicategory. But now if mod is if mod here is like this infinity 2 category, then homod is like the bicategory. So yeah, I'm using notation.
Oh, I see. Okay.
So,
okay.
Why last I changed notation from 2 categories to infinity 2 without kind of making this clear. So there was a comment. Okay, I see. You might look at the pitch. Yes. Aha, cool. Yeah, I mean, yes, I mean, I'm aware of this, but they don't use the language of shadows, right? But they do prove the results. Yes, I agree with that. As a matter of fact, I mean, it's cited. Okay, good. Thank you for pointing this out. Any other comments, questions?
Okay, any other?
Yeah. Sorry, yeah, this is your job. Sorry, I run my own seminars, like I get used to it. Sorry, yes, I'm a speaker here.
Okay, yeah.
Yeah, so thanks for the talk.
Thank you for attending.
I think I asked all the questions during the talk.
Yeah, you asked some really good questions. I like this. This is like, here you are. That means my talk worked. Like it made sense.
Yeah.
Like,
so maybe a quick remark from you, like, why exactly do you think that the definition of shadow cannot be done for? So there was a point.
Oh, here. I mean, here, right? But because I mean, what would it be? I mean, you have to like say, okay, it's like a, I mean, it's like a zeros, like a collection of maps. Okay, so you can say from don't know, you have B and like BXX or like infinity categories, and you have a collection of masks with infinity category B to D. And then you have some equivalence data, and then between those equivalences, you need like witness. Like, if you remember the definition of a shadow, not to go back a lot. Here, this one. This would be false, right? What I would rather have to say is that there's like witnesses that there's data.
Yes.
True cell.
Yeah.
Makes this commute. And then between those two cells, there's a true
cell.
That's the problem. I mean, I don't know. I mean, maybe there's like a way to universally do this, but a priori, I don't see it to make this work. Whereas, in like if you bicategory or tricategory, it will stop at level n or n plus 1.
Yeah.
Okay, maybe it's a good time to end the session and just thank Nima for this very nice talk. Thank you, Nima.